Hi guys, in this video we're still talking about the characterization of discrete time signals and systems, and I'm gonna focus now on several properties that a discrete time signal can hold or cannot hold. This is based on the fact that a discrete time signal xn is often based on a mathematical function which has or has not certain properties, and based on that what we're gonna define and several properties that can discrete time signals hold as well. So here I'm in this slide I'm recalling something which is known to most of us. We can define even signals, odd signals, symmetric signals, and antisymmetric signals. The definition of odd and even mostly rely on what we know from calculus courses, so it's pretty straightforward. We can say that xn is an even signal when the following equality holds. So this is the common equality which is used to define an even signal. So based on that, you could say, for example, that the signal that I define as n squared is an even signal, which is pretty straightforward because it relies on a parabola equation, and this is an even function. Similarly, we can define the odd signal with a change of sign in the equality. The definition of symmetric and antisymmetric signals are somehow less known, but it is somehow a generalization of the two previous lines above. This is pretty clear when you take a equals 0. We can get back to the even and odd signals definition. So, for example, in the symmetric signal, the symmetry axis is on A. Okay, so A can be either an integer or an integer divided by 2. Okay, it can be either on one sampling point or exactly between two sampling points. It cannot be any place else. And for the antisymmetric signal, then the center of antisymmetry is exactly on A. So for example, if I'm talking about this signal, let's make it bounded in time, okay? I will assume that beside these points, the signal is equal to 0 everywhere else, okay? So here, for example, we can see that the value of the signal at 0 and the value at 5 are the same. The value of 1 at 1 and the value at 4 are the same. The value at 2 and the value at n equals 3 are the same. And this can be written as follows. Okay, let's see, something like that. x5 minus n is equal to x of n. So in that way, when you're replacing n with 0, you get that x of 0 equal x to 5. If you're replacing n equals 1, then you will get that x of 4 is equal to x of 1, etc. So these lines basically saying that there is an axis of symmetry, and this axis of symmetry is exactly at 2.5 between two sampling points. Okay, so this is for the symmetric signals. And similarly, let's say that now I'm going to talk about this signal, okay? Again, I will make the assumption that besides these values, the signal y of n is equal to 0 everywhere else. So here we can see very clearly that x of 0 is equal to minus x of 4, etc. So it means that here what we can write is that y of 2 minus n, 4 minus n, sorry, is equal to minus y of n. So this signal is an antisymmetric one, and the center of antisymmetry is equal exactly to 0, obviously, and it is located at 2. Okay, so this is something also which is very important to notice for antisymmetric signal. Only if A is even, like in this case, then the value of the signal itself at this point is necessarily 0. Okay, because at this point it has to be equal to its opposite value. So 0 is the only value which can do that. Now, in the slide, we're gonna see some properties which are very, very typical of signal processing. Okay, this is less related to mathematics and more related to signal processing. So the first definition defines a signal which is bounded in time, and basically a signal is bounded in time mostly when all the relevant information is in a finite time interval. So you can think about a pulse which is sampled, okay, something like this. And for this kind of signals, okay, after 3 the signal is equal to 0 everywhere. Before 0 the signal is equal to 0 everywhere. So this signal is bounded in time. All the relevant information is between 0 and 3. The rest, I wouldn't say that it does not convey information, but let's be clear, it is less interesting. So the formal definition will say that there is an n0 such that for every index which is either above n0 or below minus n0, then xn is equal to 0. This is not related to anything. Okay, so in the previous figure, for example, n0 equals 4, okay, for example. So for every n which is above 4 or below minus 4, xn is equal to 0. This definition, pay attention, this definition does not say that n0 is the tightest value that exists, only that there is a value like this, okay? Similarly, we will say that xn is a right-hand side signal if only the left side of the signal is equal to 0, and then starting n0, it starts to change and to become interesting. Okay, so obviously we can talk about a step function, but we can also think about this damped exponential, which is also a right-hand side signal, and also what is called a causal signal. Okay, a causal signal is mostly a right-hand side signal with the additional assumption that n0 is non-negative. And we can think the other way around and define similarly the left-hand side signals, meaning that they start from minus infinity to be interesting, and starting a specific time value, time index, it is equal to 0. And similarly, we can define also anti-causal signals, which are left-hand side with n0, which is negative. And xn is a periodic signal if there is an integer value n, and this is very, very important, so I'm gonna annotate it. It must be an integer. For every n, the following equality holds, which is a standard equation for periodicity. And I will add here that the smallest n such that xn plus n is equal to xn is called the fundamental period. Again, the most important word in the definition is this one. N must be an integer. Because you define your time scale as discrete, then you cannot move as you want on the time scale. You need to move by integer steps. So here, the period and the fundamental period, they all must be integers. For example, in this exercise that we're going to solve in class, we can see that x1 is a periodic signal, while x2 is not a periodic signal, although both of them rely on a periodic function, which is cosinus t. Okay? So this we're going to solve in class, but it is very important to remember that even if the definitions about signal properties are similar in the continuous time and in the discrete time, they have slight differences which are related to the discrete time scale. That is all for this video. So in the next video, we're going to focus on systems. Thanks.